All right, good morning. Welcome back to class. So just a couple things, logistics. The homework one was released yesterday on Compass, or I mean your grades were released. The solutions are posted now. Let me just make sure that's true. Okay, solutions are posted. One thing to note is I had some questions in office hours about shadow on specular surface, which I didn't really answer directly. But just in case you were wondering, so the easiest way to check to see if it's possible to see a shadow on a specular surface is to think about, have you ever seen a shadow on a mirror? And you haven't, if it's a full mirror. And the reason is because a shadow is a dark spot on a surface where light came in from one direction and it didn't hit that surface enough or not as much light hit that surface due to being blocked from another object. And so when it was diffusely reflected, less light was reflected into your eye, and that causes the shadow. In a specular surface, the only light that the object blocks is the part of the surface that the object occludes anyway. So you can't see any shadow from the object. So if light is coming in from this direction and it hits the vase here, that light would not hit your eye from this reflection anyway because it's not reflected in your direction by the specular reflection. So that's why specular surfaces, you can't really cast a shadow on a fully specular surface. Homework 2 is due on Monday, and homework 3 should be out by next Tuesday. I just changed some of the deadlines, so homework 3 I'm actually giving you another week because there's a significant structure from motion component to it, so to make sure you have enough time to do that. Homework 4 is also pushed back a week, and homework 5 is also pushed back a week. And as I'll get to a little bit later, I also made some modifications of the final project guidelines. Any questions about homework, general logistic kind of questions? So one thing about grading is it's not, so if the grader made a mistake or didn't see something and gave you no points for it, then it's fine to ask for a correction. If you think you should have gotten 2 points off instead of 3 or 4 for a mistake, that's not really a contestable thing because everybody needs to get graded the same way. And it's also, you can imagine that if 15 of you come back to the graders and say I want 2 more points, that's a lot of time to spend on with almost no impact. So really the only contestable things are if the grader marked something wrong but it wasn't wrong, or somehow didn't see your answer somewhere for some reason, even though it was clearly there. So just a couple of notes. So there was this, you could submit your results for edge detection. Many of you noticed that if you don't do suppression, non-max suppression, then you get better results just because of the way the evaluation code was set up. But the best scoring methods tended to use another feature space other than RGB as well. So some used some used LAB space. Others used HSV space. I have to say that smoothing and hue is finding gradients in hue is kind of a weird thing because it's not it's a circular space. So 1 and 0 are both red, and you'd get the strongest gradient between a red and a slightly different shade of red. But sometimes things still work out. So these are just 3 of the top methods that I'm listing here. They mainly use different color spaces. So final projects, I want to remind you that eventually you'll have to do one, so you should start thinking about it. One thing that I changed in the guideline is that instead of submitting a 4 to 8 page report, you only need to submit a 2-page abstract, and along with whatever you present for your poster. So for example, if you make a big poster, then you could submit a 2-page written report and your poster. And if you If when you do the poster, you do it as like a set of slides, which is also okay, then you just submit that set of slides under one PDF and the 2-page abstract as the other. So you don't need to repeat illustrations that are in your poster in your abstract, but the combination of the abstract and poster should be enough to understand your project. Also, I guess I talked about some of these other things, but you're encouraged to work in groups. So you might be able to do like a bigger project that has more components with more people. And even bigger than 4 I could consider, but there would have to be some clear structure so that you each have a role. And I think these other things I've already said before. The proposals are due after spring break. So I also wanted to just mention a couple more things in detail about registration before I move on to the next section. One is that we talked about kind of simple transformations like affine and perspective and translation. One other that's worth knowing about is thin plate spline, which is a more general, a deformable representation. So it's basically combining a global affine warp with smooth local deformation. I mentioned it briefly, but just to give you a little bit more detail. So this is the thin plate spline transformation. You have, you're trying to, it's couched as trying to minimize the difference between your corresponding points, so the predicted versus actual, and also trying to minimize some regularization term on your warping. So you want to try to, as much as possible, account for the correspondences using an affine warp, but you're also allowed to do these local warps, but you pay some regularization penalty for that. And then the solution to it actually has a closed form where you've got your affine warp, and then you've got a local deformation according to the distance from the control points. The control points are the correspondences that you have. And then the other one that's worth going into a little more detail about is non-rigid point matching. So non-rigid point matching actually solves for a thin plate spline deformation. So some of you might have noticed if you try to do the alignment of your airplanes, you're not going to get an exact alignment because it can't be fully accounted by an affine or perspective transformation or whatever other global transformation you're using. But if you do a thin plate spline, then you can account for it. So you can see here, for example, it's showing like a warp from a flat worm into like a bunched up worm. And it's able to kind of, you can think of it as like pulling up the worm like by this point here. So it's a combination of an affine transformation where you kind of squish the worm and then you pull it up. In cases where you have more extreme distortion, like here, it actually incorrectly solves for the transformation according to our like semantic knowledge, because it can use an affine transformation to kind of fit most of the points just by making the worm really short and fat and putting it on its end. So it's still, as you get more complicated deformations, it tends to be harder to correctly fit the parameters of those. All right, so finally we can go into the next section of the class. So we're about 1/3 of the way through this semester, and we've covered a lot of fundamentals that are all how do we analyze images within the image or across images, but not really yet dealing with how images relate to the world. So we've talked about how they get their intensity, how we can find patterns, measure things from them with filters, how we can detect edges, how we can find correspondences across images, how we can work between images. But now we're going to look at how we can map between an image and the 3D world, or map from the 3D world to the image. So often this lecture, in many computer vision courses, this would be the first lecture of the course, because it's the image formation, the geometry of the image formation. So it's the other, besides like image filtering, it's kind of the other pillar of computer vision. So we're going to be able to answer things like which ball is closer. It's not something that you can do based on image measurements. You need some kind of model for the camera. How tall is some object in the scene? How high is the camera? What's the rotation of the camera? So what are the extrinsics of the camera? What is the position of the camera with respect to the world? And what are the intrinsics of the camera? What is the focal length of the camera? So these are things that we can all solve once we understand camera models and perspective geometry. So today we're talking about mapping between the image coordinates and the world coordinates, and in particular the pinhole camera model, which is the simplest but most commonly used model for camera projection. And we'll talk a bit about projective geometry, including vanishing points and vanishing lines, and then finally the camera projection matrix, which is the mathematical model for how we project from 3D points into image coordinates. So first, let's talk about image formation from the geometric point of view. So let's say, as a very simple idea, what would happen if you just took a film and you held it up to the scene? Then what would you see on that film? So let's say the tree is the scene here. What would you see on the film in this case? Yes? A blurred image. Right. You would just see kind of like the average light of the scene, and it would, of course, be kind of like overexposed if you didn't block it out quickly. Because if you just had the film in front of the object, then a point on the scene would project to every point on the film if it's diffusely reflecting. And likewise, another point on the scene would also reflect onto all different points of the film. And so every point in the film would just be seeing some kind of sum of the light across the whole scene. So the simple solution is that we put a barrier, and then we put a little hole in the barrier. And then, even though the point on the object is still reflecting light in all directions, only light from one direction passes through the barrier and into the film. And then if you've got a different 3D point on the scene from a different direction, then only light from some other direction will pass through the barrier and onto the film. So once we put this barrier with a little hole in it, then every position in the film corresponds to the light coming from one particular direction in the scene. So note that any point along this ray will still cast light onto this pixel. So we can model this with what's called the pinhole camera model. So we've got, and I'll just draw it out in a little bit more detail. So this is something that definitely everybody should learn. All right, so the model is, we've got some 3D scene point here at x, y, z. And we've got our pinhole over here. This is the camera center. And then I've got my image plane here. So this is like my sensor. And then the difference from the camera center, which is the pinhole, and the sensor is the focal length f. And you can measure the focal length either in meters, which would be like measuring it in terms of thinking of the sensor as some little block that's a couple centimeters wide, or you can measure it in pixels. Either way is fine. And then you think of the sensor as having a pixel width. Okay. If you were to pass a point perpendicularly through the pinhole, if you pass a ray perpendicularly through the pinhole, it will intersect at the image at a position called the principal point, which we denote U naught, V naught. And then this is usually considered the z direction. And then y is often considered the vertical direction, and x is the horizontal direction. But depending on your graphics convention, y and z are sometimes switched. So we've got a 3D point in x, y, z. It projects along a ray, put it really far away, through the pinhole, and it intersects at some pixel coordinate that I'll call uv. Oh man, stop moving. So what we want to do is we want to estimate the position uv from the 3D coordinate given a focal length and the principal point. So we can do that with similar triangles. So if we just look at the YZ axis, or the YZ directions, and the UV directions, so what we've got is something like this, where we've got Y, Z, this is U, U naught, and we'll say this is just 0. So this point is at, I guess what I mean is that this point is at YZ, where Y is the vertical length, Z is the longitudinal length, and I've got this distance here, which is U minus U naught, and I've got this distance here, which is the distance of the image plane to the pinhole, and that distance is the focal length. So now we want to solve for, whoops, let me just switch this to V. V. Right, so V is usually the vertical coordinate and U is the horizontal coordinate. So, so now we want to solve for V given Y, Z, F, U, U naught. Okay? So you can see that we've got a similar triangle here, right? These angles are the same from basic geometry. And so we have y over z equals equals v minus v naught over f. So v minus v naught equals fy over z, or v equals fy over z plus v naught. And the same thing if we look at u. So if we look at u, it's going to be in terms of x and z. So we have u equals fx over z plus u naught. Now this is assuming that the camera is in world coordinates, meaning that the x, y, and z that we're talking about, that in that coordinate system, the camera is at 0, 0, 0, and the main axis of the camera is shooting down the z-axis, or the line perpendicular to the image plane is along the z-axis. So we'll get into some more details later, but this is the basic pinhole camera model. Right. So sometimes you'll see, so if you note in this way of illustrating it, the image plane is actually, the image is actually upside down because it gets inverted, because high points in the scene will project lower on the image plane. Obviously, that's easily rectified in a camera just by showing you the bottom rows on the top. Sometimes people will draw, to deal with this, sometimes people will draw the pinhole behind the image plane, which isn't physically correct, but it doesn't really, all the equations will still hold. So you can draw that pinhole as behind the image plane, and then everything is projecting through the image plane onto the pinhole. That's another just common way of rendering the camera. So the idea of the camera, of this pinhole model, actually dates way back to Moti in China in 470 BC. So there it was like, there's a written record of it. And the first record that we have it being built was by Alhazen, who wrote a book of optics in about 1000 AD. And that book of optics eventually made its way into Italy and Europe by about 1400, and it had a lot of influence on artists in the Renaissance area, where people started to try to create more realistic and geometrically correct art instead of like symbolic art. So here you can see the idea of the camera obscura. Camera obscura just literally means dark room. Camera is room, obscura is dark. And the light projects through a little hole on the wall onto a screen, and then you can see an image of the outside world onto that screen. So there's also, there's a few camera obscuras that you can find in places like Chapel Hill. So you can go in there, it's completely dark, but then all the light is coming through a single pinhole, so you see an image of the outside world onto wherever that light is projecting. And then lens-based camera obscura was invented in 1568. So this was actually used as a tool for teaching artists to draw. Here the camera is that you've got light coming into the pinhole here. It can be focused by a lens so that you get more light in than you would if you just had a little hole. And then it reflects off the mirror so that it's uninverted, and then the tracer can kind of look at the scene and look at this and get used to drawing in perspective. It's like if a kid or even older people often, if you try to draw a scene and you're not trained in art at all, you always want to draw like a table as being a rectangle. It's hard to get used to, when you first start drawing, it's hard to get used to perspective, that actually you're not observing rectangles as being rectangles, you're viewing them in perspective distortion. So this is the first photograph. The oldest surviving photograph was taken by Joseph Niepce, and it took 8 hours. So there's a pewter plate, so it's a more slowly reactive surface taken from I think it's a rooftop. And then later, Niepce teamed up with Daguerre, which they created a more quickly reacting film, which made it possible to photograph people if they held really still for like half an hour. And then, of course, eventually the films got much better, and so now we have cameras. You can just take a picture in a quarter of a second. So you can think about the camera as a dimensionality reduction machine. You've got all these 3D points in the world, and so you've got separate objects, and they all have their distinct locations. And then everything gets projected onto this 2D image plane, and now everything kind of becomes more complicated perceptually. So things that were rectangular are sometimes no longer rectangular. The sizes change. Now you've got occlusion. This is a whole tree, but you only see some little piece of it. And so a lot of the challenge of vision is undoing all this confusion due to kind of just projecting everything onto 2D and then layering it. On the other hand, you can imagine that if we didn't have this, if we had true 3D sensors and we're seeing behind walls all the time, life would also be extremely confusing because you would just have so much overload on your senses that you would need a lot of processing power to figure out like what's actually relevant and to make sense of it. So in a way, we're lucky that we're limited in what we can see. So projection can be really tricky, so there's a lot of illustrations of that. This one is this sidewalk drawing artist who makes drawings that look from a certain perspective, makes it look like it's 3D, while he's actually just like drawing on the sidewalk. So here, this drawing looked from this perspective, looks flat, which it is. And from this perspective, it looks like he's standing on a 3D globe and he's got like 3D letters and so on. So what do we lose exactly when we do this perspective projection? One thing that we lose is length. So you can't measure which of these is closer based on their 2D distance. And actually this causes, even though we as people live in the 3D world, we have a lot of problems with that. So we tend to also measure things in our visual field or be biased by the length in the visual field. So it's hard. We would tend to say that maybe like this green ball is closer than the red ball because it's closer in our visual field. But actually, I would have to actually do the measurement to see which way it is. This game is called bocce ball, where you throw the white plane, and then the red team throws balls and tries to be closer, and then the green team throws. And whoever's further out gets to throw next. So if you're playing with one other person, then you have to keep on estimating whose ball is closer in order to know whose turn it is. And when you're first doing it, you have to keep on like walking out with a stick or something to measure. And then as time goes on, you get a little bit better at measuring, at estimating the distance between these objects along the ground plane. But this green ball could very well be further away than the red ball, even though it's closer in 2D. Also, you can't tell who's taller just by measuring their height in the image. So length is not preserved. If an object is twice as far away, then it will be half the height. Also, angles are not preserved. So this is a rectangular court, but these angles are not right angles. These sides are parallel, but the lines intersect in the image plane. So we lose angle information, where at least it's not the same angles as we had in the original 3D scene. And the main thing that is preserved is that straight lines are still straight. So all these lines that are straight under a pinhole model will still be straight in the final image. So one important concept and tool that we can use is the idea of vanishing points and vanishing lines. So the idea of vanishing points is that all lines that are parallel to a given 3D direction will intersect at a single point in the image plane. So in this case, there's these two rails, and the side, you can see also like the line formed by the sides of the grass, they all intersect at this single point. And likewise, if you had like telephone poles going down here at a fixed height and drew a line across the telephone poles, that would also intersect at this same point. So that's called a vanishing point. And then if you were to draw lines across all of these ties, these railroad ties, the wooden planks, then all of those lines would also intersect at some point in the image plane. Although if the direction is exactly parallel to the image, then that point will be at infinity. So we have vanishing points and vanishing lines. So sets of lines that are parallel in 3D will intersect, or all the lines that are parallel in 3D will intersect at a point in the image plane. And points that have a different direction will intersect at a different point. And if you have two sets of lines in different directions that are parallel to the same plane, then they'll intersect along what's called the vanishing line of that plane. I'll show you more illustrations later. But so for example here, these lines will intersect somewhere along this line, which is the horizon of the ground plane. So it'll be way over there. So they won't necessarily intersect in the image, just in the image plane. And then if I had another set of parallel lines, say that we're going in like this direction, they would also intersect somewhere on the image plane. Any set of lines that is parallel to the ground will intersect at the vanishing line of the ground, which is the horizon. So you can do, so let's say that's happening here. What is the relative length of this, assuming that these are parallel lines that are intersecting at some vanishing point in the ground plane? What's the relative length of these two segments, the red segments between the blue lines? It's the same, right? Yeah, so if these lines are parallel and intersecting at this vanishing point, then it means that that this is a parallelogram. So the length of these two lines has to be the same because these lines are parallel in 3D, and the length of these two lines also has to be the same. Let me just make a couple of points. All right, so So if I want to draw a set of parallel lines in 3D, I can pick my vanishing point and then draw lines that intersect at that vanishing point. Now, what if I have, like, say, some other object here, and the line in that direction also intersects at the vanishing point? So here I've got 3 lines that are intersecting, where if I continue them, they intersect at the vanishing point. And I might even have, a tall building here. So how do I know which of these lines are, or can I know, or how do I know which of these lines are actually parallel? So can I know which of these lines are parallel? Let's simplify, shorten the possible answer. I think some people are shaking their heads. So yeah, you can't, there's no way to know, well, unless you know something else about the scene, you can't know. So these lines, I sort of drew them as if they're parallel, but you have no idea. You can imagine taking that line and pulling it up along that same direction in 3D, and it would still keep its line, but it would be changing its 3D direction. And this, I kind of gave it away by drawing it like it's a little building or block, and then you would assume that it's vertical. But if you had a line on the ground, it would occupy the same space, or it would occupy the same part of the visual field, but then it would be parallel to the ground. So the implication is only going one way. If you have a set of 3D parallel lines, they will intersect at a point. But not all lines that intersect at that point are parallel. And so you can kind of guess that, you can think about, like, well, what are the chances that this line would happen to intersect exactly at the vanishing point? And that might give you a guess at its 3D direction, or what other lines it's parallel to. But you typically need to include some other kind of scene information to be confident about it. So the projection of 3D parallel lines intersect at a vanishing point. The projection of parallel 3D planes intersect at a vanishing line. If you, like the ceiling, the ceiling I think is flat maybe. So ceiling and floor will intersect at the vanishing line of that planar direction. If you have imagine going by a whole set of walls. All those walls will intersect at some vertical line in your field of view. If, I think I said all this stuff. Yeah, and also, so a vanishing point corresponds to a 3D direction of a line, and a vanishing line corresponds to a 3D orientation of a surface. So here's another illustration on an image. We've got all these lines that are parallel. Note that they don't have to be coplanar, just parallel to a 3D direction will intersect at some point. And then all these lines that are also parallel will intersect at another point. Note that the orange lines and the purple lines are each parallel to the ground plane. And so the vanishing line of the ground plane is the line that passes through those 2 points. And then if I had another set of lines that were parallel to the ground plane, like, for example, these lines on the, these lines on the sidewalk here, then these will also intersect at some point on the vanishing line of the ground plane. And then these lines are in the vertical direction, and if the camera is facing those lines directly, they'll intersect at infinity. And we have a way of representing that without using infinity. So, so here's another example. So what are the main vanishing lines here? And what are the main vanishing points? I can see some people going through the motions. Yeah, so there's a set of lines over here, right, that are going in the longitudinal direction on both sides of the buildings. And those will intersect at some point maybe around here. Also, these lines are in the same direction, so these lines along the curb. And then there's some vertical lines along the sides of the buildings in here, which will be, let's see, camera's facing down. So those, I think, will intersect very high up. And then there's these horizontal lines on this building, which will intersect really far to the side. So if we want to estimate the vanishing points, then we can do so by drawing a set of lines or by automatically detecting lines and then trying to find groups of lines that intersect near some point or that, yeah. Now, a couple notes on how to do this. So usually it's better, if you have many lines, then you can often estimate the vanishing point with better accuracy. But one easy mistake to make is to try to, I mean, these lines will typically not intersect at the exact same point, so you want to find some point that's close to them all. And one way that you could do that is just to find the mean of all the intersecting points, but that's a really unstable way of computing their intersection point. You can imagine if they were closer to parallel, there might be some lines that are parallel, and then you get like a point at infinity, or that are just really close to parallel, so you've got some intersection points near infinity and then others that are much closer. So instead, you want to try to minimize, if you're estimating a vanishing point, you want to try to minimize the angular distances between the lines and the point. So you choose a point such that the angle between that point and the midsection of the line segments is as close as possible to the angle of the line segment. And that will give you a more stable estimate of your vanishing point. So you can also have vanishing objects. As objects get far away, they get really small. So you can get, it's another cue for depth. If you've got like some, a bunch of rocks on a field, then you can get some sense for the orientation of the field based on the rate at which the rocks get smaller as you go up in your field of view. So vanishing points, we'll do more with them later, but they're often used, they can be used by themselves to calibrate the camera and to make measurements in the scene. So that's something we'll get into, I think, on Thursday. So for now, let's go back to the projection. So I talked about this, this projection from 3D point, which I'll denote x, y, z. So I'm going to try to always, well, I'm going to break this in the next slide. But I'll usually try to use capital X, Y, Z for the 3D point and lowercase uv for the pixel coordinate. So I'm going to try to use uv instead of like xy for the pixel coordinate to keep a distinct notation for 3D scene points and 2D image points. All right, so we've got our 3D point. It's projecting through a camera center, which is at some, maybe translated. It goes, it hits the image plane at some point uv. And we can compute u and v given x, y, z, u naught, and v naught. So the equations that I gave you before are these like nonlinear equations, right? It was v naught, or v equals fy over z plus v naught. But we'd like to represent things in linear coordinates, or as a linear system of linear equations. So a convention that we can use is called homogeneous coordinates. So where Euclidean coordinates store a particular point, homogeneous coordinates store a direction. So it's a point up to a scale. So if I want to convert x and y to homogeneous coordinates, then it becomes xy1. And if I want to convert xyz to homogeneous coordinates, it becomes xyz1. If I've got some point x, y, w in homogeneous coordinates, and I want to convert it back to Cartesian coordinates, then it becomes x over w, y over w. And this becomes x, y, z, w becomes x over w, y over w, z over w. So this is like this is encoding the scale. And this is a convenient notation for for modeling projection, because remember that anything along a ray will intersect at the same point in the image. And so when we represent a point in the image in homogeneous coordinates, we're really representing that 3D ray. And note, so it's invariant to scaling. So if I multiply x, y, w by k, then when I convert back to Cartesian coordinates, I get the same thing as if I hadn't multiplied by k, assuming k is not 0. So point in Cartesian is a ray in homogeneous coordinates. And then there's also, we have ways of representing lines in homogeneous coordinates. So remember that we represented this line equation earlier when we were doing model fitting. And so this is, there's a lot of conveniences to this. So we can represent a line as ax plus by plus c, or as just this 3-vector, ai, bi, ci. Below that, I'm showing how to convert from a pixel coordinate into a homogeneous coordinate. You just append a 1 to the u and v dimensions. If I want to compute the cross product of 2 points, if I want to compute the line that passes through 2 points, I just take the cross product of those points in homogeneous coordinates, and that gives me my line ABC. If I want to convert it to the form where I have, where A and B gives me the normal, then I just can normalize A, B, and C so that the magnitude of A and B is 1, where the length of A and B is 1. And then if I want to compute the intersection of 2 lines, then I take the cross product of the lines. So it's nice that in homogeneous coordinates, it's just really simple to compute the intersections of lines or the lines that pass through a pair of points. We can also, in homogeneous coordinates, represent points at infinity. So if I try to represent the intersection of these 2 lines in the blue lines in Cartesian coordinates, I would just have to say it intersects at infinity, and I can't really say anything else. The red points also intersect at infinity. But if I can represent it in homogeneous coordinates as that the blue lines intersect at 1, 1, 0, so they have a direction of 1, 1, and it's infinitely far away. And the red lines intersect at 1, 2, 0, which is infinitely far away in a different direction. And if I took the cross product of these 2 lines, I would get 1, 1, 0. So you can then deal with points that are infinitely far away or parallel lines intersecting at some known direction but infinite distance. Okay, so finally, let's go back. Let's take that notation of homogeneous coordinates where I represent a point up to a scale, or in other words, I represent the ray that a point came from, instead of just representing the single point itself, and use that to model projection. So before I get into that in more detail, I want to show some examples of the application, because I'm about to get into a lot of math, so let me show why it's worthwhile. So I'm just going to show some cases where I've used this projective geometry. When I first took computer vision, I was interested in recognition. I never really thought I would need to know projective geometry very much. But actually, it's turned out that I've used it all the time in many different applications. So one case is in object recognition, where we showed that by modeling the projection and saying that that most of the objects are on the ground, and so if we just estimate the horizon of the ground, then we can tell about how big an object should be given its distance. Then we can improve the accuracy of object recognition. So if I think that I see like a little person here, I know that that detection is incorrect because it's the wrong size for that position. And then once I've detected the objects, then I can plot their 3D positions along the ground plane. Another example is in single view 3D reconstruction. So I was interested in trying to estimate geometry from a single view. And then once you estimate what parts of the scene are the ground and vertical, then we can use knowledge about just simple knowledge about projective geometry to create 3D planes and then render the scene from different views. Or if we want to try to estimate spatial layout in indoor scenes, we can use vanishing points to estimate the direction of the camera with respect to the walls. And that gives us a rotation. and then we can solve for the translation by trying to fit lines to the boundaries of the wall and the floor. And then by finding pieces of the objects, then we can create a little 3D volumetric representation of the scene. Or if I want to put things into pictures, then I have to know what the, I have to be able to model the geometry of the objects and room so that when I put other objects onto those surfaces, they move along according to that 3D geometry and cast shadows on those objects. Likewise, if I want to try to estimate a scene in more detail and try to fit 3D objects to the scene, or take multiple images and try to create 3D models of the scene from those images, I need to know geometry. So geometry, this perspective geometry is of course important for any kind of geometric application, but even many different kinds of tracking and recognition can benefit from understanding the projection. Okay, so earlier, let me switch back to this for a second. So earlier we modeled that u is fx over z plus u naught. Now using homogeneous coordinates, I can create a simpler model. So I can say, or I can create a linear model, I should say. So now I have my point x, y, z, and what's this? I'll walk through this in a little more detail, but first let's just spit it all out. UV. Okay, so I'm going to write it like this. So now I've got what here is my intrinsic matrix, which I'll walk through in more detail. But now if I multiply this out and then convert back to Cartesian coordinates, I've got here WU equals fx plus u naught z, WV equals fy plus v naught z, and w equals z. So substituting z for w, I get, I'm running out of room, I'll just do it for this equation, uz equals fx plus u naught z. And then dividing both sides by z, I get u equals fx over z plus u naught. Right. So now I can represent this nonlinear equation, fx over z plus u naught, with this linear equation in homogeneous coordinates. And that makes a lot of processing much more convenient for us. So now I can solve a lot of things as systems of linear equations, as we'll get to later. So let's walk through that. So first, actually, let me just go. Okay, let me go back. All right. So this is the overall model. So we've got a 3D scene point, which is here like a big bold X for X, Y, Z. And our camera has some rotation and translation that maps from the world coordinates into the camera's coordinate system. We mainly need that if we're trying to model multiple cameras in the same world, or if we have some reason to care about, say, the ground being like on a y equals 0 plane. Then after this maps from the world coordinates into the camera coordinates, then the K, which is the intrinsic matrix, which is composed so far of the focal length and the principal point, projects from the 3D coordinate onto the image coordinate. And so this will be in homogeneous coordinates, and if I want to get the pixel coordinate, I just divide the first two values of x with the third value. So here the important notation is that this is the world point. This is the extrinsic matrix that projects from world coordinates into the camera coordinates, still a 3D point at this here. Then this is the intrinsic matrix that depends on the internal camera parameters like focal length and the size of the sensor. and really the focal length and the principal point, which is the center of the sensor. And that projects onto the image coordinate. Blah, blah, blah. OK, so let's start with a really simple model. So let's assume first that the principal point is at the center of the image. And we're going to just say that the center of the image coordinate is 0, 0. So then we're going to assume first that that the camera is already in world coordinates. So we don't really need a separate coordinate system for the world and the camera. We're just going to say that the center of the camera is at 0, 0, 0, and the camera is looking straight down the z-axis. So here, our model is quite simple. We just have this 3D scene point, x, y, z, 1. And then this projects onto, if we do the math out, we'll get w u equals fx plus z, and w equals z, which will give us u equals fx over z, and then u naught is 0. Okay, so the same equation that we had earlier. Similarly for v. So now let's remove an assumption, and let's say that our principal point is not at 0, 0 anymore. So we'll often assume that the principal point, I guess there's a couple reasons we could do this. So one is that instead of saying that the center of the image is at 0, 0, we might want to say that the center of the image is at some pixel coordinate, like 320, 240 for a 640 by 480 image. Another reason that we might want to do this is that if you've cropped an image, then the principal point will be far from the center. So then you actually need to estimate it. And even if you haven't cropped an image, then it's often not exactly in the center. It might be a little bit off. And so you might want to estimate it, although it's a difficult thing to estimate. So here we get the equation that we had before, where we have u equals fx over z plus u naught. Now I can remove an assumption that the pixels are square, which we don't usually need to remove that assumption, but sometimes for like a scientific application, you might have an imaging device that has more resolution in one direction than another. And so we can model that by, instead of having a single focal length, we have two of them, basically, one for the x direction and one for the y direction. Or you might think of this as we've got a focal length and then some scale parameter. Whoops, sorry, move. Sometimes I move the cursor on my own screen and then it doesn't show up over here. So we can model this as like a focal length and a focal length times a scale, or it's just two separate parameters. Sometimes these are also called fx, fy. But this would model if like your pixels were, if your sensor cells were rectangular, not square. Now we can also remove one more assumption and say that the pixels might be skewed. And this is mainly to capture some kind of small mechanical error in the manufacture of the camera. So usually skew would be because the sensor is not exactly perpendicular to the lens. And so you get some distortion from that. So often it's safe to say that these are both f, the focal length, and that this is 0. And usually we just estimate f in the principal point. Sometimes we even say that the principal point is at the camera center without trying to measure it. So if I work out that equation now, well, actually I won't work it out. But so if you multiply this out, you'll get wu equals ax plus sy plus u naught z, and w equals z. So then dividing u out, you'll get that u is now a function of both x and y due to that skew. So now that's the entire pinhole model. So this models a projection from a 3D point onto the image plane as a linear projection. Lines will be preserved. I'll mention later that there's also a possibility of radial distortion. So if you've got like a fisheye lens, or if you've got Or if you're projecting onto a curved surface, then the pinhole model doesn't apply exactly, and then you need to apply some kind of, then you need to also estimate radial distortion parameters. And then first you use those distortion parameters to unwarp the image into something that fits a pinhole model, and then you can apply this model from then on. Right, so that's the intrinsic matrix, K. Now let's look at the extrinsic matrix. So the extrinsic matrix maps from a point in world coordinates to a point in camera coordinates. So first, translation. So note that, let me just write some of this out. Let's go back to our simplified formula. UV1W for the intrinsic matrix. So I have F U naught V naught 1. And then I've got a 3 by 3 zeros for, identity, sorry. 3 by 3 identity matrix for my rotation, and then I've got Tx, Ty, Tz for my translation, and then I'm multiplying this by XYZ1. So this part here will just give me x plus Tx, y plus Ty, z plus Tz. No 1 anymore. And then when I multiply this out by W UV1, or when I multiply this out by the intrinsic matrix, then I get U equals Fx over Z, Fx plus Tx, Z plus Tz, plus U naught. So all the translation vector does, sorry about that, in and out. All the translation vector does is it substitutes x plus tx for x and y plus ty for y, which is what you would, if you think about it, what you would expect a translation vector to do. So it's a 3 by 1 vector. Now I've also got this rotation. So the full form that we usually care about is that I've got WUV1 is equal to my simplified intrinsic matrix times some rotation and translation. So this is a 3 by 1. This is a 3 by 3, but it only has 3 parameters because it's 3 rotation angles. So it's got a lot of constraints on it. And then this, of course, is a 3 by 3 with 3 parameters. So this is that the point is being rotated and then translated and then projected. So there's an alternative representation, which I think I'll mention later when I'm talking about structure from motion. But note that this is not representing, this T is not the center of the camera in world coordinates, and the R is not the angle of the camera in world coordinates. It's a mapping from the world coordinates to the camera coordinate system. If you want to map from the camera coordinate system to the world coordinate system, you just need to do an inversion. So you end up with, well, if I remember correctly, you end up with RC is R inverse, and TC is R inverse T. I think that's right, but I'm just doing it from memory, so I could be wrong. So this would be the rotation of the camera in world coordinates. So since R is mapping from world to camera, if I want to map from camera to world, it's the inverse of R. And then T is the position of the camera in world coordinates, which you can solve by just using this portion and then setting that this is xc, yc, zc, and then solving for the translation from xc, yc, zc back. Right. Actually, you can solve, well, anyway. So let me switch. Don't want to get too sidetracked. Okay, so you can represent this as a as a combination of rotations about different angles. So here, this is showing the rotation about each axis, but keep in mind that the order in which you apply these matters. So if you do Rx times Ry times Rz, that gives you a different result than Rx times Rz times Ry. Right? Like if you rotate around this point and then rotate here, it's different than if you rotate here and then rotate around in the other axis. So we'll usually just represent it like this. We've got all these intrinsic parameters. There's 5 of those. And then we've got the intrinsic parameters, the rotation and translation. Even though it's a 3x4 matrix, there's only 6 real parameters, the 3 rotation angles and the 3 translation values. And so in total, this we can also combine the intrinsic and rotation matrix to create a single projection matrix, which will have 11 free parameters. And so that's a fully parametrized matrix because in homogeneous coordinates, everything is up to a scale. So a 3x4 matrix with 12 parameters will have at most 11 free parameters, because if you just multiply it by any k, it should give you the same result. It'll just change w, which we divide out at the end to get to Cartesian. So, so as another example, we can use this to project a point at infinity now. So we can take our vanishing point, represent it as a 3D point at infinity, and then compute where it will project to in the image plane. So for example, if we knew that given the rotation and translation vector and intrinsic parameters, if we know, we can project where all the vertical lines in the image, or the lines that correspond to the gravity direction in the image, will project in the image plane. So this is showing so here we've got our 3D point at infinity. Note that because the infinity is because there's a 0 scale parameter, so when I divide by these, they go to infinity. Note that when I multiply it by RT, t has no effect. And it's true that the vanishing point does not depend on your translation. So if I'm looking down a field or looking down like a railroad line and I see that it intersects at this point, if I just move my head from left to right, that point will not change in my field of view. Only if I rotate will the point change in my field of view. So all cameras that have the same rotation will view the same vanishing point at the same position. And so doing the math out, then I can get down to, I can multiply my rotation by the XYZ point, and then the point at which I observe it is just projected from this rotated point by the intrinsic matrix. So we can actually, I may get into this later, we can actually use that to solve for the camera parameters, because if we have figured out what is the vertical vanishing point and what are the other vanishing points that are perpendicular to that, then that gives us 3 equations from which we can solve for the camera intrinsic parameters, F u naught and v naught. So this is just doing out that math. So that's just something worth noting. And one other case that is worth noting is something called scaled orthographic projection. So you might sometimes hear about like an orthographic image, which is if you have like a view from the air onto the ground, and you just have the ground laid out like a map where everything is just a scale, and you don't have any perspective. So everything is like on a flat. You're looking at like a flat plane, then that's orthographic projection. So the idea of orthographic projection is that you're just mapping every point xy is mapped onto u and v just according to some scale parameter, and the distance away from the camera has no effect. So that's often used as an approximation for far-field objects. So, for example, this car, when it gets really close, is just kind of a scaled version of itself. Because they're both kind of far away from the camera, the shape of the projection, or the shape of the object when it projects on the camera, doesn't change much as the object gets closer. It just gets bigger. So looking back at this equation, we would say that the shape of these 3D points stays the same as we project onto u and v. It's just determined by the size of it is determined by some scale parameter. And then as the object gets even closer, then it breaks that assumption that that perspective is not having a large effect. And now we need to use full perspective model to really account for the shape of the object that we observe. So back here, even if I move an object from left to right, you still kind of just see that shape of the front of the car without much change, just a change in position. But as you get closer and you move from left to right, then you see different parts of the car. And also now you're seeing like the front of the car is, like the front wheel will be bigger than the back wheel because of the perspective. So often when we do object recognition, we say that we have a single model that applies to an object anywhere in the scene. So we'll have, like, say, some face detector that assumes that, that all faces look the same no matter how big they are and where they're located in the image. And that's making a scaled orthographic assumption. So it's assuming that the objects are kind of far away. If somebody sticks their face like right in your face, then the appearance of their face will be different than if they're much further away. You'll get, like, their nose will look really big because it's even closer. So this is what I was mentioning, that so far we've covered what's called the pinhole projection model, that you've just got this nice clean geometric projection of rays from 3D through a pinhole onto the image plane. And that's the model that we'll usually work with. And when we can't work with it, we'll usually try to solve for some distortion and then undistort the images so that we can go back to the pinhole model. But there are many cases when you do have some other kind of distortion, like when you have a fisheye lens, or you could even have a spherical lens, in which case you'd have a spherical camera, in which case you would have a different model altogether. But you can have like this pincushion distortion, which is where things kind of get like stretched out at the corners. Or you can have barrel distortion, where things kind of get compressed at the corners. And usually these distortions are due to the lens, not due to like some failure to make a flat sensor plane. So commonly you have like 2 to 4 additional parameters that account for this distortion. All right, so we covered a lot of stuff, but these are the main things to remember. There's a concept of vanishing points and vanishing lines, which we'll use later. So this is the idea that if you have a set of 3D lines that are parallel, then they'll intersect at some common point in the image plane. If you have 2 sets that are parallel, where each set is parallel to the same plane, then each set will intersect at some point on the vanishing line of that plane. If you have a set of planes that are parallel to each other, then they'll intersect at some line in the image plane, which is the vanishing line of those planes. And so the vanishing point corresponds to a 3D orientation, and a vanishing line corresponds to a planar orientation, or a surface normal. And then we have this pinhole camera model and projection matrix, where we have a 3D point, and we model it in homogeneous coordinates. That projects, first we rotate it and translate it into the camera coordinate system. So if we have different cameras at different positions, then let's say I take a video camera and I move it around, I'll have the same intrinsic matrix everywhere, but the rotation and translation will change as I move the camera. So I'm mapping from the world coordinate into each of these camera coordinate systems with a changing rotation and translation. And then once I've mapped into the world, into the camera's coordinate system, then I can project down onto the image plane using the intrinsic matrix, which may be held constant if I've got a video camera without changing the focal length. And to be able to model this mathematically, we're working in homogeneous coordinates, where it's important to remember that if I've got some coordinate like w times xy1, then that's modeling a ray rather than a point in Cartesian coordinates. So all the 3D points along that ray will project onto the same homogeneous coordinate in Cartesian coordinate. So next class, we're going to talk about the applications of the camera model in projective geometry. So we'll talk about how we can recover the camera intrinsic and extrinsic matrix parameters from an image, how we can recover size in the world, and how we can project from one plane onto another plane. Thanks.